So now we're going to complete an example that it goes way back to Unit 2, Lesson 3, where we had tanks mixing and we used our modeling expertise to come up with a system of equations, but didn't show you how to solve them yet. So,
that stuff coming up.
Yes. So here's the problem. Tank A has an inlet pipe flowing at 3 gallons a minute and an outlet pipe filling tank B at 4 gallons a minute. So if you can go back and look at that where I just copied it, example 6. Tank A has an inlet pipe 3 gallons a minute, outlet pipe 4 gallons a minute. So you're coming in fresh water, out 4 gallons per minute of somewhat briny water into tank B, where 3 gallons runs out into the gutter and 1, oh maybe it's going into a fish tank, who knows, 1 pipe gallon per minute coming back into tank A. So it's an unusual mix. So if both tanks hold 50 gallons and tank A starts in the beginning with 25 pounds of salt and tank B contains no salt initially, further assume the fresh water is entering tank A left 3 gallons per minute. We made our model. If you go back, you would see if x of t is the amount of salt in tank A, t minutes after fresh water starts flowing in, and y of t is the amount of pounds of salt in tank B. These functions can be found by solving the system of equations. Okay, dx dt, look, this is rate in 3, amount of salt in 0, plus rate in 1 times the amount of salt in this tank divided by 50, right? Because that's the percentage of salt in that 1 gallon, right? So, and then minus the 4 gallons that's going out, and that's the amount of salt divided by 50. That's the, again, the salt per gallon. That's what this was, salt per gallon. So that's dx dt. dy dt is, well look, that is coming in, 4 times the amount of salt per gallon. 3 gallons is going out and into the gutter, and the amount of salt in that is the per gallon is y of t over 50, right? That's the salt per gallon. And then 1 is also going out, but it's going into this other tank. So the positive coefficients represent salt coming in, the negative salt going out, and the system simplifies to this one with the given initial condition. Okay, here's the system. dx dt is just 1/50th y of t minus, I wrote that 2/25 because I reduced the fraction, x of t. Okay, and dy dt, simplifying, that's 2/25 x of t minus 2/25 y of t. And the initial conditions at the beginning, there's no salt in tank B, and there's 25 pounds in tank A. So we're going to solve this one using determinants. This is the system. Look, 1/50th. If I added this to both sides, I'd have d plus 2/25 applied to x, and then minus 1/50th applied to y equals 0. So here is that set of derivatives in the numerator. The second one says dy dt plus 2/25 y, so that's 2d plus 2/25 y, and for the x part it would be just this negative 2/25. So there's the coefficient matrix applied to x. And since we're finding x, we would replace the x column with the zeros that are on the right side of this system of equations. I didn't write it like that, but I guess I should have done that. I hope it's okay if you want to mentally write it with 0 on the right. You'd be okay. I hope that's all right.
I can't take this.
Well, then go ahead and take the time and pencil it out if you're having trouble with that. So, of course, the right-hand side, if you got a column of zeros, well, and it's going to be 0, right? Technically, I guess I should say this is a determinant here, and so bear with me 1 second. There. That should be the determinant there, and of course the determinant is 0, so now it's good. So we now know we've simplified the whole thing just down to these differential operators applied to x equals 0. And so that means d plus 25 squared, see this times this, right? And then minus a negative, or minus a positive, so it's going to be minus, wow, 2 over 1250 applied to x equals 0. And similarly, you can do the same thing, replacing this column with zeros instead. D plus 2/25 squared minus 2 over 1250y equals 0. We need only solve one of these, and the hard part is going to get down to two parameters. Let's see what happens when we do that. We solve this one, multiplying this out and collecting the like terms. It factors d plus 1/25, d plus 3/25 applied to x. See, multiply this out, and you get this. Sorry, not this. It's going to be 4 over 625, and 4 over 625 minus 1 over 625 is 3 over 625. The 1 over 625 is really this. So, and it does factor. I don't know if you could see that. It factors in a kind of a nice way, you know. And so the characteristic equation has roots negative 1/25 and negative 3/25. So we've got a solution with too many constants, x and y. C1 either negative 1/25 t and C2 either negative 3/25 t. Y is the same, only with a C3 and a C4. Well, we've got to find a relationship. So let's substitute in the first equation. That's this one. So dx dt, here's that. You know how to take those derivatives without a hitch. Equals 1/50th of the y, there's that, minus 2/25 of the x. So we substitute all that in there. And when we collect the like terms, let's see, the like terms that have C1 in them. Actually, the like terms that have is not C1, it's the like terms that have e to the negative 1/25 t. So we got negative 1/25 C1 equals 1/50th C3 minus 2/25 C1. And similarly, negative 3/25 C2 plus 1/50th C4 minus 2/25 C2, and that's an equation, and that gives us enough that we can get the relationship. See that from this one we've got the fact that 1/25 C1 equals 1/50th C3, so C3 is twice C1. Nope, I got that wrong. Twice C3 equals C1. So maybe I'll say it like this. C3 equals sorry, I'll get this straightened out here in a minute. 1/2 of C1. So this should be 1/2 of C1. My error there. There. That fixed that. And so let's see if I have the relationship right on this side too. So see, I had 1/50th equals 2/25 minus 1/25 C1. So 1/25 C1 equals 1/50th C3. So C3 is half of C1. Okay, and this one, let me see. Add this to both sides. We've got negative 1/25 C2 equals 1/50th C4. And did I botch that again? Why, I did. So C4 is negative 1/2 of C2. So I'll fix that up as well. There. Now what I haven't done yet is apply the initial conditions. Well, that might be a little different now. So x0 is 25. All right, put in 0. We get e to the 1. Okay, put in 0. I'm sorry, we don't have e to the 1. We have 1. E to the 0 is 1. So c1 plus c2 equals 25. Okay, now here's a little problem. This should be 1/2. Oops, sorry, I did it backwards. This should be 1/2, and it is. This should be negative 1/2, and now it is, but it doesn't make any difference because this equation shows us that c1 equals c2, and so they're both equal to 25 halves. And so, saved myself there a little bit. Nope, here's a problem. This would be 25 fourths. And this would be minus 25 fourths. Okay. They give the amount of salt T minutes after the mixing. Can you tell by looking at your solutions what amount of salt will be in each tank after a long, long time? And is that what you expect? And the answer is, yeah, well, that T go to infinity, then this is going to go to infinity. And this is going to go, sorry, it's not going to go to infinity, it's going to go to 0, and so is this. So eventually, how much salt's going to be in tank B? Nothing. How much salt's going to be in this one eventually? Well, T gets to be big. E to a big negative number is approaching 0. E to a bigger negative number is also approaching 0. So we're going to have no salt at all.
I am so glad.
Good.